So I wish you really all of success, best of success for this workshop. And yeah, I will again welcome you to this event and hand back to the organizers. Thank you very, very much for being with us.
Okay, thank you very much.
Thank you.
And we are we're very happy that we had the opportunity to organize this. I'm very grateful. And okay, yeah, thank you.
Thank you.
Thank you very much.
Yeah.
I think.
Yeah, I mean, now we can maybe move on to the talks themselves.
Okay.
So yeah, so okay, let me move on to the first talk by Yacine Mehtar-Tani from BNL. So Yacine is going to talk about jet quenching and possible quantum applications. And Yacine, if you can share your screen or your slides.
Yeah, just sorry, just a second. Okay. All right, so let me see. So you see my screen?
Yes.
Okay, I'll put it full screen now. Okay. All right, shall I start?
Yes, when you're ready. Yes.
Okay, thank you. So let me first thank the organizers for putting together this very interesting workshop. And it's really timely in our field. So it's a nascent topic. I mean, connecting hard probes and heavy ion collisions in particular to quantum information science. So in my talk, I will talk about jet quenching and try to convince you that in fact this this problem is amenable to somehow information, quantum information, and trying to put this into this type of frameworks. So let me first give you an outline of my talk. So I will briefly introduce the physics of jet quenching. So many of you are already familiar with this, but this would serve as somehow a motivation for the talk, and then show that this problem of jet quenching, in fact, can be cast and is usually very useful to view it as a non-relativistic quantum mechanical problem. So which right off the bat can be connected directly to quantum mechanics. Then show a specific application, which is related to the building block for energy loss, which is the medium-induced radiative spectrum, and then discuss a different new way of looking at the problem by investigating quantum entanglement of jets in the quantum plasma. So I will focus on leading order calculation to show that, in fact, this provides a new viewpoint to the problem. I will end with a few remarks, and in particular saying a few words about also the applications to quantum computing. So let me first say a word about heavy ion collisions and why they are a special system to study. So you can see here in this picture here the different phases of heavy ion collisions. So this is the initial state where you have these two kind of Lorentz contracted heavy ions that are about to collide. And right after the collision, a large number of degrees of freedom are freed, and mainly a very dense medium of gluons is formed initially, which interact very strongly towards thermal equilibrium, and then of course leading to this hydrodynamic behavior that is seen in the data before hadronization happens here at freeze out. So this is a very, very interesting topic because it somehow allows us to investigate many aspects of QCD. So there are emergent phenomena that have been attracting a lot of interest in the past decades or so, and like collective behaviors that is somehow the hallmark of the hydrodynamics. And turbulence, plasma instabilities, the approach to thermalization, and all kind of anomalous transport. So this is a very interesting system to study, and hard probes are used, in fact, can be used as tools to study and probe this system here. So I mentioned the soft probes. So there are two types of probes. So we have soft probes that typically looking at particles of the order of a GeV or so, close to the temperature of the plasma, which is of the order of 500 MeV, say for the LHC heavy ion collisions. So this is where collectivity happen. This is around, so the density of particles is very large. And this is probed via the flow harmonics, the so-called VNs. But then you have hard probes, which typically happen at transverse momenta of the order of 10 GeV upwards, so from 10 to the TeV, in fact. So jets are measured at almost a TeV scale at the LHC. And those hard probes are produced in a rather small number in the collision compared to the soft probes. And they can be treated as perturbations in the middle of this quark-gluon plasma. And by measuring those probes as basically test particles going through the plasma, one can learn about the properties of the plasma. And this is the motivation of using hard probes such as quarkonia or high PT hadrons, and of course jets, which is going to be although all of these three topics are connected in some way or another, I will focus on QCD jets. Okay, so jets were instrumental, and not only jets, high PT hadrons were also instrumental in the discovery of the quark-gluon plasma. And this was seen at RIC in the early 2000s in the strong suppression of high PT hadrons in gold-gold collisions that you can see here. So by measuring the nuclear modification factor, which simply measures the ratio of the yielding AA collisions to PP, there's a typo here, properly normalized by the number of binary collisions. In the absence of final state interactions, we would expect that after the production of high PT particle, it will simply fly in vacuum, and we would expect the ratio to be 1. And the strong suppression here indicates the existence of the creation of deconfined matter of quark gluons that somehow interacts strongly with the final state high PT particles. So this was also confirmed by the LHC by measuring fully reconstructed jets. You can see here again, as I said previously, the jet spectrum here spans really very large range of scales up to TeV scale. You can see here, and the suppression is rather large. So this is quite interesting question. So we are measuring TeV scale jets that are strongly suppressed, although there is a wide range separating the scales jet, which is a TeV, and the medium scale, which is of less than 1 GeV scale. And this wide separation of scales leads to all kind of wide range of phenomena that are responsible for taking the energy from the hard modes in the jet down to the medium scale where thermalization occurs. So as you can see, this is just a cartoon to show a digest event in proton-proton collisions where jets are produced as nascent partons here that fragment in vacuum. So to speak, you can really look at this and probably here can say a word about the quantum nature of this kind of entangled system. So this is a completely a coherent initial state where the jet would fragment in vacuum. There'll be all kind of correlations here. While when such an event happen in the middle of a dense medium, we might expect all kind of phenomena like color randomizations and the destruction of quantum coherence that might be very interesting to study, besides simply the probing the transport properties of the plasma. So there are techniques that are designed to study observables in colliders, PP collisions, or in electron proton nucleus collisions, which are based on QCD factorization. But in the context of heavy ion collisions, because of the strong final state interactions, such as multiple scatterings in a final state, the existence of underlying events due to the also the many proton nuclear collisions, as I mentioned, color randomization, decoherence, and multi-part interactions. All of these somehow combine to somehow make the standard factorization approach fail. This doesn't mean that there is no factorization. It simply means that the leading twist approach, which is the expansion around vacuum, simply fails in this context. So we need to really resort to new techniques to account for this final state interactions which require resummation of those multiple interactions in the final state. And in fact, the situation is not really hopeless, because we, by moving away from the vacuum expansion point, we are putting ourselves in a situation where we can use statistical techniques and go in a region where the calculations can be, in fact, dramatically simplified, and by, as I said, invoking the thermodynamic limit. And this is what we usually do in this context when we compute jet observables, in particular the jet quenching and the nuclear modification factor and associated observables. So as I mentioned it, you can wonder here. So of course, the production of multi-jet event here, one of the properties of such an event is the fact that they are all kind of entangled, in a sense, also in a color sense. So there are all kind of color connections that connect all of those final state colored particles, and the existence of a dense color medium in a final state will tend to destroy this color coherence, and this is something that could be investigated in the future in this context of quantum information science. So what to expect? I already said a few words about this. So we have a large number of degrees of freedom, and we don't measure all the particles. So although the initial state must be a pure state, what we measure is essentially going to be mixed states. So we have a jet, for instance, will be immersed into a plasma, and because we don't measure, even a jet is not measured completely, we will end up having a mixed state in which somehow would require to define the tools and the observables that will allow us to investigate this quantum information that would be hidden in those mixed states, which also can be used to study the properties of the system that is not measured. So all kind of questions: quantum decoherence, entanglement, and quantum or classical thermalization can be studied in this context, and also color randomization. So before maybe going back to the problem of quantum information that is encoded in jet quenching, let me maybe first introduce what the underlying processes or the elementary processes that make up the interactions in the final state. So to leading order, a jet would be a fast particle that go through the color medium, and during its propagation, it will suffer multiple scatterings, in particular color randomization, rapid color randomization, which is somehow a result of this exchange of gluons in the T channel with the plasma. And because the jet has a very large component along the longitudinal component, and the medium scale is much smaller than the energy of the jet, the typical propagation will be small angle propagation. So the deflection of the jet is rather small, and the transverse momentum acquired via those multiple scatterings is rather small compared to the energy. So this can be described after a certain number of assumptions, such as independent multiple scattering approximation. We end up having this kind of classical picture of Fock-Planck equation where the probability for acquiring certain transverse momentum in the plasma is given by this diffusion-like equation, where the diffusion coefficient is the so-called Q hat. So the transverse momentum squared, the mean transverse moment squared, will increase linearly with time, and in fact will increase linearly with system size equivalently, which is the size of the medium here. So this is the first elementary process. This is elastic process, which is responsible for transverse momentum broadening. But then those multiple scatterings also can trigger radiations. Although the problem of momentum broadening isn't apparently quantum, the process of radiative energy loss is quantum, is inherently quantum, and it's related to the so-called LPM effect here. So as I said, multiple scatterings will conspire during a quantum mechanical time here, which is given by the uncertainty principle here to be omega, the frequency of the radiated gluon divided by transverse momentum squared. During that time, the gluon would be somehow delocalized, and multiple scatterings would act as a single scattering, one effective scattering to put the gluon on shell and then of course produce it. And this would, during this time, the transverse momentum acquired by the gluon can be simply estimated using this diffusion coefficient Q hat times the time of the formation. This will give us a typical formation time of that medium-induced gluons, which is simply equal to the square root of the frequency divided by Q hat. So the spectrum of such medium-induced gluon, which we could expect to be simply proportional to the coupling constant times the number of scattering centers. Because of this quantum mechanical destructive interference effect, the proportionality would be with the number of effective scattering centers, which is no longer the actual number of scattering centers, but rather the number of somehow the number of scattering centers divided by the typical number of scattering centers that act during one radiation here. So this effective number of scattering centers decreases with increasing formation time. So when the formation time is of the order of the system size, the entire medium would act as a single scattering center, and this is where we get maximum suppression of the spectrum. So here you can see it. So this number of effective centers is scaled with system size divided by the formation time. That's how we would estimate that number. And this leads to this 1 over square root of omega suppression. So at very low frequencies, where the formation time is of the order of the mean free path, this is the so-called Bether-Heitler regime, where all of the scattering centers would act independently. But as omega increases, we have this coherence, destructive interference, which will lead to the suppression of the spectrum. And at high frequencies, we reach maximum suppression. So this is really the building block for radiative energy loss in jet quenching, which is purely mechanical. So the standard, maybe a few words also on the formalism here. So the standard way of computing observables in colliders is to use factorization or S matrix, where we basically use asymptotic states in a fully covariant formalism. But in this context of jet quenching, because the medium is extended, we have an extended medium, and then we can really introduce the notion of a time evolution. We can show that using light front formalism, the system somehow the system can be described by 2+1p non-relativistic quantum mechanics. This is simply really equivalent to using the light front perturbation theory. So, in a few words, what do we actually do? Suppose we have a parton here, gluon, that branches multiple times in the medium. So that would depict a jet evolution in the plasma, and then multiple scatters, and then radiates extra medium-induced gluons. That would be the picture. This is the time variable. So because most of the branchings will occur collinearly along the direction of the jet, so we can study the evolution of the jet along the z direction, close to the light cone and use the light front description here. And then you can see for a given time t, which is of the order of z. So we have, this is x minus the light cone variable x minus close to 1. This is close to the light cone. The system can be described by on the transverse plane. So you have transverse position here, and just kind of a projection at a certain time, where now our color charges are evolving in a 2D space here, and in the presence of a random background field. So now the medium can be described by a random background field here, which is only function of the time variable and the transverse position. This is how we can map the problem of jet evolution in plasma to that of 2 plus 1D non-relativistic quantum mechanics, simply because the choice of light cone variables allow us to express the Hamiltonian in a familiar form, which is the momentum operator square divided by 2 times what is the analog of the particle mass, which is here the p plus, the plus component of the momentum, which is conserved toward the evolution. So to be more precise, so here's the light cone. This is the x minus x plus direction where the jet evolves. So the jet has a very narrow extent in the x minus direction, is given to 1 over p plus. P plus is very large. So that's the momentum of the longitudinal momentum of the jet. And during the evolution of the jet inside the medium, which moves in the opposite direction here, the x minus direction, after boosting, of course, the medium in the other direction. The medium is at rest, but we can always boost the system to look like a collision of head-on collision. And because the jet is a narrow object, the x minus dependence of the medium field is very weak. So it's x minus is close to 1. So that's why we can simply drop the dependence on x minus and reduce the problem to really 2 plus 1D. So the interaction of the jet particles or the fast particles with this background field is iconal. So the k plus momentum of the exchanged gluons with the plasma is much smaller than p plus. So that's the largest scale of the problem is the p plus component of the jet. And then the interaction would be reduced to this iconal vertex here. So it's simply proportional to a minus component of the background field, which is roughly proportional to delta k plus. There's no exchange, k plus exchange with the medium. So in terms of some scalings of the different components of jet particles, so this is momentum of a jet particle. So the p plus for an Onset particle, we have k perp squared over 2p plus for the minus component. And that would scale like lambda squared, lambda being simply defined as k perp over p plus. And because k perp is much smaller than p plus, lambda can be treated as a small parameter here. And of course, k perp is of the order of lambda. So k perp here, why it is small, so k perp is typically of the order of the transverse momentum acquired during the propagation. And that's simply, as I said, by diffusion is q hat times L, and which typically would be of the order of 5 GeV, which is much smaller than the jet energy, which would be of the order of 100 GeV to the TeV scale. So there's a separation of scales between medium scales and the jet modes. So another simplification happened at the level of the propagation of the propagator of, say here, for instance, discussing the Dirac propagator. So that's because of the conservation of the spinel helicity throughout the propagation, the p plus component, the Dirac propagator simplifies dramatically. So the Dirac structure, which encodes all of the spinor structure, factorizes in this simple structure. We end up having, without really going into much details, we end up having this the Dirac structure factored out, and then all of the dynamics would be encoded in a scalar propagator. So we have this kind of this Klein-Gordon equation with this potential A minus. So this is not yet transparently related to 2+1D quantum mechanics, but there's one step from this equation, which is scalar equation for the propagator, to get to a quantum mechanical description. So again, because K plus is neglected in this, the exchanging K plus with the medium is neglected, there is an invariance under translations in X minus. We can use this to fully transform the scalar propagator, and that's how we get this Green's function here, which depends only on transverse positions, a time variable, and of course, which implicitly depends on P plus E. Here E is P plus, so which is conserved throughout the evolution. That's why it's ignored here. And this is simply the evolution operator of quantum particle evolving in a potential. And this obeys this 2+1D Schrödinger equation here, as you can see. So this is simply the kinetic term. This is the potential, and the Hamiltonian, in terms of the Hamiltonian, you can simply write as the free part of the kinetic term of the Hamiltonian and interaction potential here. So this is very familiar, and this is basically what we need in addition to of course, interactions that do not conserve number of particles like splittings. But if we ignore for the moment splittings, this is all we need to describe the propagation of a particle in a plasma. So we have a particle now which propagates in a transverse plane in this stochastic background field, and now we need to account for the fact that stochasticity of the background field. We need to average over the ensemble of all of the configurations of such, and this is where the connection to open quantum systems appear. So before performing such an ensemble average for a given configuration, of course, the evolution is unitary. But because, of course, at the end of the day, we'll end up recording many events, we will actually perform such an average, which will alter this unitary evolution. We end up having a mixed state in the final result here. So let me point you to the talk by Dia on Thursday, who will in fact discuss in depth the connection of jet quenching to open quantum systems using an alternative approach, although quite overlapping with this, using in particular the soft collinear affective theory approach to jet quenching here. So to compute observables, I said we need to average over medium configurations. And this is in general quite difficult. And but in certain approximation, if we assume that we are in presence of a weakly coupled plasma, so the coupling constant is much smaller than 1, we have this hierarchy of scales where the length of the medium is much larger than the mean free path of a particle in the plasma, which is given 1/g², T being the temperature of the plasma, which is much larger than the screening length. So typically the interactions will be completely independent from each other. And then we have this kind of classical Markovian picture of interactions. Then we can use, this can be described by Gaussian white noise. So the 2-point correlation function here of the background field can be described by a local interaction, the delta function of T minus T prime, and proportional to the elastic cross-section here. So this elastic cross-section, which is to leading order just 222 matrix element, and which can be computed for a thermal medium, particularly in this case, when the transverse momentum exchange is much more smaller than the temperature, we simply get this form here. And at large transverse momentum, it's simply proportional to the number of density, the density of scattering centers divided by the Q perp to the 4th, as you can see it here, 1/Q perp to the 4th, which is just the standard Coulomb tail here. So this is all we need to perform medium averages of observables for jet quenching observables. So, all right, so we can use this now to go and compute, for instance, the radiative spectrum, which encodes the LPM effect. So this is just an example to show how we would go about doing such a calculation. So the system, so it's very convenient to, instead of computing an amplitude and then squaring it, by folding the complex conjugate amplitude on the amplitude by looking at the problem in a way that is very akin to the Schwinger-Keldysh contour. So you have a particle, a fast initial particle that goes through the plasma. This is evolving in time. And then in the complex conjugate, the same particle moving also with time here in the same direction. Why it is very convenient to do this? It's convenient because this allows us to immediately see how the instantaneous correlations that we were introducing here, right, this data can be accounted for. So as you can see, then we have a certain time t, a radiation of a gluon, and then starting initial state having this kind of two-body system would turn into a three-body system with a gluon, quark, antiquark that interacts with the plasma, and then we would be correlated via this the medium average here. All right, so the amplitude, well, the cross section, so to speak, here is simply given by the propagator here of the gluon, which is non-iconal propagator that I described initially, and then the fast-moving quark and antiquark can be simply described by a Wilson line. This is just a path-ordered exponential, which accounts for the color precession of the particle. This Wilson line also is encoded in this non-iconal propagator, which is just a generalization of the Wilson line in the for a particle that explores the transverse plane, so that accounts for quantum diffusion between the time t1 and t2. So the quantum somehow nature of this process is encoded in the gluon that somehow is radiated by classical currents that are frozen in transverse space. Those two currents are frozen in transverse space, while the gluon can explore via quantum diffusion the transverse plane here. So integrating over the final state transverse momentum, measuring only the frequency, reduces this color structure into a two-body system, because this quark and antiquark just collapse to gluon. We have just a gluon, which is non-iconal, and then the Wilson line in the adjunct representation here, and then we just trace this object here, then average over the medium configuration. So we can average then over medium configurations, and we simply get this formula for the medium-induced radiation, integrating over the time, radiation time in the amplitude, radiation time in the complex conjugate. Then we have this kernel here, again, which is just this Green's function, which obeys, again, a Schrödinger equation with imaginary potential, which is related to this two-point correlation function, or the elastic cross-section. Potential proportional to q hat times the transverse coordinate, transverse size of the which is a conjugate to the momentum transfer with the medium. So this is a typical form, so to speak, the leading order perturbative form of this potential, which is x perp squared times a Coulomb log here. This is looks like being quite simple formulation, yet it's quite difficult to solve exactly the problem with this form of the potential, although it can be solved exactly if we assume that the log varies very slowly, and then we have a harmonic oscillator, which can be solved exactly analytically, allowing us to resum multiple, to all orders, the insertions of this potential. So we'll have really multiple scatterings to all orders. But we will fail in doing so in capturing really the hardtail, the Coulomb tail at high transverse momentum. To capture that, we would need to keep the full potential and perform the calculation iteratively, order by order, in this potential, and this is the so-called opacity expansion. So this opacity expansion treats this imaginary potential as a perturbation. But again, this approach is valid only at high frequencies. So to kind of combine the two, we can use a so-called improved opacity expansion, which would split the Coulomb logarithms into leading constant contribution, which is log q squared, introducing this kind of factorization scale q squared, which is expected to be of the order of the typical transverse position squared here. So this log would be large, and this log would be small. And then this is kind of shifting the expansion point from vacuum to harmonic oscillator. So we can resum this the harmonic oscillator to all orders and treat this as a perturbation. And then the result can be done. Of course, we can compute this order by order, and the leading order is just the standard harmonic oscillator result. And the next to leading order in such an expansion will account for the Coulomb tail. And you can see it here in this numerical evaluation of the spectrum, where the full blue line here is an exact numerical solution to the problem. So that was obtained from this paper, courtesy of Apollinario et al. And then compared to the opacity expansion, this is the dotted line. As you can see, at very high frequencies, it kind of tends to the exact result, but then at low frequencies, it diverges. And in fact, this expansion is divergent at low frequencies. And then you see the leading order. That's the first term here. That's the red. That's the green curve here, and it's below the. Doesn't do really quite well, but captures the essence, the qualitative features of the soft sector here, but fails completely at large frequencies. But then adding the second term, which accounts for the Coulomb tail, simply provides for a dense enough medium, a rather good description of the full result. Okay, so this is a typical tool to so to speak, a building block of jet quenching calculations. So let me now move to really the topic of this, more aligned with the topic of this workshop here. So as I just said, the jet problem in heavy ion collisions somehow is amenable. It's natural to think of this problem as an open quantum system. So we have an initial parton that can be seen as a quantum system that evolves in and interacts with an environment, which is the quark-gluon plasma. So naturally, we would like to answer a few questions. So what is the density matrix of such a jet in the medium? What is the entanglement entropy of the system? So what is the quantum informations encoded in such a subsystem? So the reduced density matrix, of course, is obtained by tracing out the environment, which is here in this case, simply by performing an average over the configurations of the plasma background field. So system B being here the medium. So this is what's traced out. Doesn't have to be thermal. It could be also cold nuclear matter. For instance, just a collection of nucleons in a nucleus, or a parton that would go through nucleus and interacts with suffer multiple scatterings in the. This could do it as well. Doesn't have to be thermal. And then system A here that we'll observe is the jet. So, of course, solving the problem all orders in perturbation theory is very complicated, and this is probably our ultimate goal. But we can already learn a few things when focusing only on the leading order. So we just forget about gluon radiation. So by starting just preparing the system to be, of course, a pure state, consider a parton that has a transverse momentum which is strongly peaked around a certain initial transverse momentum, typically of a certain scale, which we can think of as an inverse scale, much smaller than the final transverse momentum that is accumulated throughout the evolution. So we have a peaked initial condition. And then, of course, this pure state will evolve for a given configuration via the evolution operator. To leading order, this evolution operator is just our Green's function, this propagator that takes a particle. So particle number is conserved on one particle that simply evolves in this background field. So this is what we get for the density matrix. It's just simply, again, here, this is the initial density matrix. And then we have the two evolution operators expressed in the transverse momentum basis here. So initial transverse momentum, we have 4 momenta, of course, because we have 2 for each matrices here. And then we have to average over the transverse, over the medium configurations. And this is how we end up having a mixed state. All right, so at late times, of course, this can be evaluated, right? We can use as I said, the model for this Gaussian model for medium averages to evaluate the density metrics. But we can already say a few things about such the late time behavior of this density matrix. So what we expect is quantum decoherence and the emergence of classical behavior. And when this happens, the density matrix would tend to diagonalize. And by using this assumption, simply using this assumption, diagonalization of the density matrix, which can be expressed simply as a delta function, proportion delta function of kf, which is the transverse momentum variable here, and then a color space also, so diagonal and color space times this the eigenvalues in momentum space. Then we get simply under this assumption, it's just straightforward to show that the density matrix simply tends to this form here, this diagonal form, where this pk perp is simply the Brooding probability, which is kind of a classical object that obeys the master equation. So this transverse momentum probability is time evolution is given by this rate equation, where gamma q perp was introduced early on with in this, which is related to the elastic cross section. And then, of course, in the diffusive approximation, we simply get back our diffusion equation, which relates which makes the dependence on q hat apparent here. All right, so we can compute again the von Neumann entropy, and in this late time behavior, then the von Neumann entropy will tend to the differential Gibbs entropy. It's simply this integral over k times log mu squared pk. So mu squared here appears naturally simply to make the argument of the log dimensionless. So then it's very simple. So just give a very simple application here. Let's assume we are in diffusion approximation. So the transverse momentum, the transverse distribution here is simply given by Gaussian, which is solution of the diffusion equation. And one finds that the entropy scales linearly, logarithmically with time here, as you can see here. So it increases logarithmically with time. And of course, it would be interesting to see how this behavior would set in, how this classicalization would set in by solving exactly the quantum problem, or computing fully this von Neumann entropy by fully evaluating the density matrix in this model. All right, maybe to conclude a little bit, let me maybe point you to a topic that I didn't cover here, which also is studied quite a lot recently. So I will just point to two works, which will be discussed by Felix later this week, which is using quantum supremacy to compute jet observables on a quantum computer. So so hopefully this field will evolve quickly in the future. But those initial studies just set the ground for possible improvements. And here in this specific study, it was the Lindblad equation was simulated for haprobes in general in a thermal bath, where they used a simple time model of a two-level system just as a proof of concept to show that we can study, in fact, haprobes in plasma and on a quantum computer. And this P not observable here can be viewed as the time evolution of the nuclear modification factor, and this will be discussed in Felix's talk. There's another approach to jet quenching on a quantum computer, another strategy to kind of put jet in a plasma on a quantum computer, which was put forward by Joao and Carlos, where their goal was to be able to measure momentum broadening compute moment programming on quantum computer. So the approach was hybrid and somehow in line with what is discussed here in my talk, which basically solve the part and going so for this time evolution operator on a quantum computer, which is just this the time evolution operator here on a quantum computer for a given configuration of the medium color charges, which are treated as a stochastic variable, which is of course computed classically. So for each configuration, we would somehow compute it on a quantum computer. So that's a very interesting study here. So two studies that I guess will be covered by Felix in his talk. So this is all promising. And as I said, this is a nascent field, which is promising in many aspects, whether it's regarding the quantum computing aspect or whether we're interested in quantum information encoded in jets. But there's a lot to be done to really somehow really extract all information or really learn all what can be learned in this field, and it would be interesting maybe to motivate also a little bit the discussions during the workshop, especially when it comes to jet quenching, to maybe put a certain questions and maybe items here that I think are interesting. So one of the questions is whether we can simulate fully momentum broadening on a quantum computer leading order process. So of course we have strategies. The question is whether we can do it in a foreseeable future. And then probably the most important goal here is to tackle high order corrections. We can do leading order calculations, but real life is really quantum in all sense, and we would need to, of course, go after multiple partner systems. And this is somehow the holy grail of this field, and not only for heavy ion collisions, but also in PP collisions, where we rely a lot on event generators, where a series of approximations are used to kind of transform a quantum mechanical field theoretical description into a classical Markovian branching process. But if we were to be able to simulate at the amplitude level the branching process, which would encode all of the quantum information, particular quantum interferences and so on and so forth, we would be able to go beyond what is achieved in current event generators, which are written at leading log or next to leading log accuracy. We would go beyond that by encoding all high order contributions. So as I said, this is relevant for PP collisions and also for heavy ion collisions. As I said, the picture of a system that evolves with time is natural here, and would be interesting to see how one could encode on a quantum computer the multi-partner system that now makes up the partner shower in the plasma, and study all kind of physics that relates to energy loss and in heavy ion collisions. And of course, the question of quantum information, jet observables at high orders. So the onset of quantum and color decoherence in heavy ions. So this is a question which is, I think, really at the core of our field. How do we go from initial coherent quantum system into a system that is completely decoherent? How is this quantum decoherence setting in to set the stage for thermalization? In most of the our descriptions of thermalization of hydrodynamization, we start, like in the bottom-up scenario, we start with invoking the analog of molecular chaos assumption used by Boltzmann, and that sets the initial condition for the kinetic description. But the question is how we get there, and I think that's a very interesting question that would be could be treated, and we would benefit from learning from that on how we moved to thermalization from initial color glass condensate initial condition. So Anton Gilman is just one last reference here. Although the jet in the plasma is obviously a mixed state, we could, in vacuum, it also a mixed state if we if we remember that we don't measure all of the partons in finite state, and also because it radiates soft gluons that are color connected with the entire event. And that so there's a study here that investigated this specific point of resolved and unresolved partons in jets and discusses the entanglement entropy in the case of jets in vacuum. So it's very very exciting field, a nascent field, as I said, and looking forward to really having very nice and exciting discussions during this week. So thank you.
Okay, thank you, Yacine, for this very nice talk. So we still have some time. So between this and the next talk, there is a 30-minute gap, so we have some time for questions. I think the easiest way is just for people to put I mean, I guess you can raise your hand in Zoom.
Yes, I see a raised hand by Michael Strickland.
Yes, so
can you unmute yourself?
Yeah, sure. Thanks for the excellent talk, Yacine. I had a question. So in the end, you were talking about, solution of the Lindblad equation for open quantum system, and then it immediately went to quantum computing. Is there a path forward that doesn't involve quantum computing in the near term, where we won't have to make so many simplifying assumptions about the interactions? I guess that's my question. Yeah.
Yes. Yeah. I think it's going to be very difficult. So here, for instance, right? So you can. So the question is. So you can always compute. So the question is how you would describe the medium, right? So you need to make certain assumptions, right? Here I mentioned this kind of Gaussian model for the medium, but given that assumption, or thermal medium, right? Weakly coupled thermal medium. If that is good enough of an assumption for you, I think you can perform calculations solving the Lindblad equation. On a classical computer. I don't think now the question is when you start really accounting for high order corrections, right? And then, right, if you were to resum multiple particle systems, right, then I don't know. I think you will certainly be able to do it if you focus on the leading contribution of such multi-particle systems. Suppose maybe leading log, if you can figure out, and then you just recast your equations in terms of resummation of certain type of contributions, and then you can reduce your density metrics into a much simpler evolution equation. But it would be, you don't want to reduce too much to end up with a Boltzmann equation, right? You don't want to go all the way down to kinetic theory. So you want to be able to really study quantum nature of the phenomenon. So I don't know. I think there is somehow an in-between. I believe there is an in-between, which is which makes this field for me interesting, right? I think we can certainly learn things. And I don't know if that answers your question, but I think it's we cannot really. It's very hard to do things without making certain assumptions to kind of simplify, be able to have tractable, formulas. In that sense, we need quantum computer at some point, but that's really in the far future. But we still have a long way to go to really, exploit those what we can do still.
Thanks. It's a good answer to the question. I was just looking for your thoughts, and maybe other people can chime in.
Yes, no, I'm not sure of the order, but I think maybe Xiaojun was first. So if you unmute yourself.
Okay, thank you. Hi, Yacine. Hi, thank you for the very nice talk. Yeah, I have a question about this page. Like you kind of project the density matrix and the evolution operators onto the momentum basis. Mm-hmm. Can I think of these momentum states as just an arbitrary basis? I can choose to project the operators onto another basis, but maybe the momentum basis is easier for the calculation to be done.
Yes, the momentum basis is a natural one that somehow is expected to be diagonal, and at late times. So because it's diagonal at late times, then you can easily, you see the classicalization, so to speak. Mm-hmm. Right.
Okay. Yeah.
But if you want to compute the entanglement entropy, you have to diagonalize, right? Mm-hmm. So at some point, and initially it's very hard, right? If you want to compute the density metrics fully, you can do it in coordinate space on another basis, right? Mm-hmm. Certainly, but eventually you would like to really diagonalize your density metrics at some point.
Okay. Okay.
And the
great.
momentum basis is kind of natural because that's the classical basis, so to speak.
Sure. Like now you only talk about the kind of leading order no radiation picture. If I add radiation into this picture, what would be the matrix element of the splitting in the momentum space? Will that be some, I don't know, like, is there a way to write down the splitting vertex in these spaces?
Yes, we can write the down splitting vertex. Yes, right. I mean, this I didn't put it here,
Okay.
but yes, I mean you can certainly write it down right. I mean, we do it. I mean, all the time when we compute multiple branchings in the context of. So the splitting is if you want to find this matrix element, you can just go into any light front perturbation theory review or paper. They usually provide those matrix elements in this type of frameworks. When
I see. Okay.
light front quantization.
Mm-hmm. Like does the vertex conserve momentum or it does not?
Well, it conserves, it conserves transverse momentum. It conserves the P plus, but not the P minus.
I see.
Right, so that's
Okay.
the P minus is not conserved in this.
Okay. Okay, gotcha. Thank you.
Yeah, thanks.
Nora and Felix have raised hands.
Thank you. I had a comment about the discussion before on the answer to the question of Mike. So what it was answered is definitely true, but I think that we can get some idea of the power counting as a structure of the correction if we use the factorization and effective field theory. So from this point of view, I'm very much looking forward to the talk of Varun using soft collinear effective field theory. And this open quantum system framework can help us in understanding class of diagrams and having information about the power counting. So perhaps we would be able to attack this problem even without quantum computing. Even if quantum computing will help. Of course, if you use factorization, that could be very helpful because you also may assume that the quark-gluon plasma is strongly coupled, and if you factorize it, then you can get some description of the quark-gluon plasma encoded in some non-perturbative correlator. And if you are not too far from equilibrium and you are moving along different scales or different temperature with time, you may use conventional lattice perturbation theory to evaluate this correlator. This is what we have done for quarkonium and maybe a strategy also for jet quenching. That was my comment.
Right, I agree. I think the way I view quantum computing is more like a technique. It's a tool, right? And you use it when it's useful. So if classical computers won't be able to keep up with the large number of degrees of freedom you want to tackle, then probably quantum computer can help with that. So so factorization is certainly going to be the go-to theoretical framework. But there will always be certain approximations. As I mentioned, you would have to perform certain summation of certain diagrams, leaving out certain others, and hopefully quantum computers will allow us, will help us to go beyond that, right? As lattice techniques help us to go beyond simply perturbation theory, right?
Yeah, right.
Okay.
I think Felix, if you want to ask a question, I think you can do it now.
Okay. Great. Thanks. Hi, Yacine. Thanks a lot for the nice talk. Actually, a question about this slide and related to that. You mentioned the work by Duff and Wouter, right, on jets, basically a vacuum, right? I was wondering if what you write down, is that related to what they're doing, or like does it reduce to what they have in mind? When you remove the medium, basically, or how should I think of the relation of what you wrote down and their way of writing down entropy for jet and so on,
Right.
or is that really conceptually different?
No, it's not different. So so in their framework, because jets are evolving in vacuum, so you have a jet that fragments many partons, and then you trace out the soft part or the large angle part of the jet. That's how you kind of go from a pure state to a mixed state, right? But now that's how you generate entropy. Here, but if you ignore multiple branchings, you have only one parton in vacuum, then obviously nothing changes, right? So there's no creation of entropy, right? Now here, when you put the same system in a plasma, you can generate entropy simply by elastic collisions, right? So you can look at what Dufdale did as simply the reference, so to speak, or baseline for this calculation, right? So if you were to go to higher orders in this calculation, because this is just a leading order, just one part, and there are no radiative corrections. If you were to go to higher orders, then we would have to account for what Duff discussed, right? Because you would have
he used like a parton shower and all that, right? Too.
Right, exactly. So you would have to try to trace out not only the medium, but also the unmeasured partons in your jet. So suppose you have a cascade of partons that is induced or not induced, even just a collinear, vacuum cascade. Then you have to, of course, to throw out certain, quanta, right, that you don't measure. That's how also you can generate entropy. So you would have like two sources of entropy in the problem.
I see. So basically, yours is basically like a leading order plus medium, and so that basically generates some decoherence. Versus in their case, like the decoherence is like multiple emissions, and then they separate that.
Right.
Basically.
Right.
I see.
Right.
Okay, great. Thanks.
Okay, and I think finally we have a question.
Yeah, I think the last question could go to Mayan.
Okay. Hi.
But I think you have to speak closer to the microphone. Or...
Okay. Hi, Yacine, can you hear me?
Yes.
Oh, okay. Thank you for the nice talk. If you could go to page 16, I have a question about the medium field. So you give a correlation function for the medium field. So I wonder if there's a way to formulate the field on the amplitude level. I'm asking this is because if one want to do a time evolution of a jet going through the medium, either classically or on a quantum circuit, it would be natural to formulate the interaction operator which needs the field on the amplitude level. So I wonder if there works do on this direction about formulating the field on the amplitude level.
Yeah, I think yes. So I think this was done in a different context, which is in the context of small x physics and saturation physics, where it's the technology is very similar. So you would somehow compute the first the amplitude, right, for a given configuration of the field. So you would sample your background field from a certain distribution, which would be Gaussian here in this situation, and then you compute your amplitude, and only after that do you take the square, right? I don't know if that answers your question, but from a operational point of view, you would do it this way, right? You sample your field and compute the amplitude, and then square it, right? And then of course sum over all many configurations. But formally, right, analytically, that's the way you do it, right? You would square and then average over using this correlation function. So probably, yeah, I would point to really numerical studies in the small x field. So they've looked at this extensively, I think.
Okay. Yeah, actually, my collaborator and I, we do the lifelong Hamiltonian formalism. So we actually use the field from the color glass condensate, which is the MV model. So there we use the field on the amplitude. I think that's what you are talking
Exactly.
about. Yeah.
Right.
So yeah.
It's
So
equivalent to the MV model. Yeah.
Okay. Yeah. So I wonder if that also apply to the hot medium of the color of the Coulomb plasma.
So say again, I didn't hear the last sentence.
Oh, so I wonder if that also apply for hot medium of a Coulomb plasma.
Right, right. Yes. So really, I mean, the technology in the MV model is the same. The only difference is what you would put in this correlator, right? Whether it's the way it's screened. You know, you see here the screening is is different from that of standard, Yukawa potential, which is used in the MV model. So these are details of modeling, I would say. But the nature of the plasma would be encoded here in this correlator. So when you sample your field, this is how you would encode the thermal nature.
Okay, thank you.
Thank you. And I think we have
yeah. There's a final question, I think, so we still have time.
By Yarjun.
Yes.
Oh yeah, thank you. Hey, Yacine, I just have a quick question. Like, since all the calculations done in the light front Hamiltonian or light front quantization way, does the time in the evolution equation have to be the light front time, the t plus or t minus?
Yes, I'm afraid. Yes. Yeah.
I see.
Yeah.
Okay.
It's
okay.
really, yeah. It has to be light front. Yeah.
Okay. Mm-hmm. Yeah. Thank you.
Well, I mean, this is, all of the quanta are moving, in the forward direction collinearly with the jet. Mm-hmm. When you move away from that region, all kind of stuff will happen.
Okay.
You have, interferences with the initial states, kind of things, So moving away from that, I don't know. I'm not aware of any, formalism that allow you to go, to move away from the collinear region of the jet, especially in this context.
Okay.
You have also problems with gauge invariance in this, try to formulate the problem in terms of, gauge invariant correlation function. So it's really not easy. Right. So that's why sticking to the, forward direction is simpler.
Okay.
Mm-hmm. Okay. I think there are no more questions, at least for now, but we can, we have a discussion time after the second talk. And now we should have, okay, before let's thank Yacine again.
Thank you.
And then now we have a 15 minutes break, and then we start again at 4:30 in Europe. Okay, let's see you in 15 minutes again.
Yes, okay.